So in order to find the vector potential, we find all of the currents in the problem, and we integrate over the volume of all of the currents in the problem at what I'm defining here as position r prime, but we're integrating over it as a dummy variable. The only time that r appears in here is down there, and that really complicates the problem, all right? But that allows us to calculate the vector potential. If we know all the currents in the problem, we can calculate the vector potential. We have another relationship that we can use, which is that if we know the vector potential, we could find the currents. So I'll write that this way. J is C over 4 pi So knowing the currents, we can find A, the vector potential, or knowing the vector potential, we can find the currents that must give rise to that vector potential. And in the end, in any classical course, classical or special relativity related course, we're interested in the magnetic field. It turns out that in quantum mechanics, it's more important to know the vector potential, because that's what appears in Hamiltonian. Right? So we need them both, but for any classical force calculation, we need the magnetic field. Right? We could calculate the magnetic field directly from the current, so I can write that down too. The magnetic field is now I could just write this as the curl because I know that, and I can just take the curl of that. But I'm writing it in this form because this is the one where I don't have to take any derivatives. And also I can just say, knowing the current density, I can solve for the magnetic field. That's the magnetic field as a function of position r, and the currents are all at r prime. Knowing that relationship up there, I can write one more for if I know the magnetic field, then the current density is
You're missing a factor, it's cubed on the bottom. And the B.
Yes, you are right. Thank you. I have it wrong in my notes.
Do I fix it before I put it up?
Yeah. Okay, then we've got, I have one relationship for the magnetic field from the vector potential. There are ways to calculate the vector potential from the magnetic field, but generally we don't use them. So I'm going to set that aside until we actually need them. But those are the relationships that, that we need, right? But first of all, there are a few tricks that I can show you this time around to find the magnetic field and the potentials, right? But in order to solve a complete problem for all the possible cases, we need to think about how we would solve for the vector potential, for example, in the presence of boundary conditions again. So I can always say, if I know all the currents everywhere in the problem, then I can solve for the vector potential in the magnetic field. But you're not always given all the currents everywhere in the problem. Right? You may be given some asymptotic field, and also it might turn out that sometimes solving for the magnetic field everywhere in space is particularly difficult. and that we really only want an approximation for it. In that case, we want to be thinking about the potential primarily, and about solving for the vector potential using differential equations. That was not very clear. I'm going to come back to setting up the boundary conditions in a minute. And I'm just looking here to see whether there's anything else that I want to write down. One relationship that follows from all of this, but that frequently turns out to be useful, is Ampere's law. The integral of the magnetic field around a closed loop is equal to the flux of the current through the surface bounded by that closed loop, right? And this is frequently a lot easier than that for solving for the magnetic field, as if you have particular symmetries, which you can take advantage of. Okay, so we have a vector potential, but it turns out that sometimes, in some special cases, you can use some tools that you're already familiar with to solve for another quantity, which is called the magnetic scalar potential. Oops. And this can be particularly useful when you're solving in some approximate case. I'm going to talk in a little bit about multipole expansions and approximations of the magnetic field due to some current that's somewhere in space, right? I'm going to talk about multipole expansions, and one of the tools that we would use when we do an expansion is the magnetic scalar potential, as opposed to the vector potential over there. Right. In Chapter 1, Ohanian reviewed some properties of vector fields. And one of the theorems that he put up that had no purpose whatsoever at that point is relevant now. And that's this one. The statement of it is this. Suppose that we have a vector field that has zero curl. Let's see. Maybe I'll call it A. Okay. That's the start of it, all right? In some simply connected region. I have to discuss what simply connected means. Then, in that region, the vector field is conserved. Suppose, I should say, if then conserved, which means that curl of A is 0, the divergence of A is 0, and so it means that del squared A is 0. It also means that there must be some equivalent to the potential that was that with the equation that we've got there, to the relationship for the field that we had before for electric fields. So I can actually write that there exists some scalar field. So that was a vector, which satisfies that relationship.
Why is del squared A 0?
Okay, so if a vector field has zero curl in some simply connected region, then A is conservative. If it's conservative, then the curl is 0. All right. So this was the statement in chapter 1, and he went about proving it. I'm just going to mention the condition that's important to that relationship. Let me see whether I wrote it. No, I didn't write the derivation here. All right. But let me just say that what we're actually doing is employing Stokes' theorem so we have the integral around a path, right, closed path. What do we mean by simply connected region? It means that if I take this path and I shrink it, then I can shrink that path down to 0 dimensions. And I'll have no flux through the path, all right? If, for example, unfortunately, I'm going to draw a similar thing. Let me draw a loop of current like this, for example. All right, so now I've got current. And then I take a path, so I'll dash my path over here. All right? And now I take a path that goes around that loop of current. Right? When I shrink my path down, I change the condition. I can't go to a point and change the current that goes through that path and keep the same current that goes through that path. All right? This region here, this example here, that particular path that I just took there is not simply connected. There's something inside it, right? And I've got to cut through it in order to change. And so I could say that out here there's no current, but there is current enclosed by that path, right? I could take another path, for example, one up here. Right? That path is simply connected. There is no current enclosed by that path. Right? And if there's no current enclosed by that path, then the relationships that I've got over there apply.
So by that A, you meant the vector potential A? Rather than the
okay,
A of
so now, let me come back over here and look for the definition of A.
No, I mean, you used 2 different A's. Isn't the...
Yes, by that A, I actually mean the vector potential A as well. That's why I chose to use A over there. The general proof can be done with any vector field A, as long as it's locally connected, right? As long as it's simply connected in a simply connected region, right? But let me come back over to here. I was searching for something. I need I thought I had a relationship for the curl of A.
Yeah, the curl of A is B. So you're saying there's 0 B
Curl
field.
of A is B, is at the top.
Yeah. No. Okay, hold on a minute. I may
That
have
doesn't-
screwed up.
So when you said A vector field A has 0 curl, you meant any random, and you actually meant B there.
I meant B.
So then it's not, then del is
Yeah.
Sorry.
Yeah, I screwed up.
Is del squared B still 0?
Vector field B and no. What that means is that, thank you. Curl of B is 0, it's conservative, all right? And Maxwell's equation tells me the divergence of B is 0. All right? That means that the Laplacian of A and of some vector potential, scalar potential, must be 0. as well. So that means that there exists a scalar potential such that V is equal to gradient of phi V. I'm not sure whether there's a minus sign in there or not, but we're not going to worry about it right now.
There is a minus sign.
There is a minus sign. Okay. And that means that, oops, L squared phi V is equal to 0. And it's also true that del squared vector potential is equal to 0. Okay, I apologize. I wrote my notes in terms of a general vector A and then confused them. All right. Which means then that all that stuff that you learned about the electric potential in terms of expressing it as solutions to Laplace's equation, and then all you need to know is the boundary condition, applies to the magnetic field and magnetic potential as well, as long as you apply it only in a region of space that is so-called simply connected. So to come back to a ring of current here, right, so if I've got a ring like that, then I can apply the solutions to Laplace's equation and boundary conditions for the upper half of this space. I can apply it separately for any region in here. I can apply it to the bottom half of the space, right? And I can apply it to the space all outside of the ring. So I could have a path like that, right? As long as it doesn't cut through, as long as this doesn't cut through the path, right? Then, or rather, as long as the path doesn't cut through the current, right? Then I have a simply connected space, right? What you can think of is that I can create, if I can find a surface that is bounded by that loop, and that surface is not cut through by current, then I can use the solutions here, right? Yeah.
If you drew the path completely inside the loop of current, but
Then you're okay.
okay, good.
Completely inside the loop here.
Just like
Any
you
path
have-
you like, as
yeah.
long as it
It
doesn't,
cross.
as long as the current doesn't cut through it,
Okay.
you're okay. Okay? In mathematics, they have a whole bunch of other examples that have to do with donuts and toroids and stuff like that. But those don't apply. Well, it's not that they don't apply, we don't need them. So we just have to worry about whether the path that we've got is cut by current. Okay. So what this means then is that in principle, we can solve for the scalar potential using the solutions to Laplace's equation in any region of space. And if we take enough terms in the series, it's going to be true, right? Or rather, if we take enough terms in the series solution, all of the solutions to Laplace's equation for a given geometry, then we're going to be able to express the full potential, and from the gradient of that, we can find the magnetic field. Right? Yeah,
So what happens when you don't have a simply connected region?
can't do this.
Okay, so then what would you do?
You might have to do that. There's no, again, it's like in electromagnetics, if you knew where all the charges were, then you could just do the integration to figure out what the fields and the potentials are, right? It's only if you don't know where everything is. But then in a couple of minutes, I'm going to actually treat this case of a ring of current, right? And it turns out that we can solve for the magnetic potential here, and there, and in here. And then we can piece those things together, and we'll have the full magnetic potential, right? So there are ways around the limitations of the apparent limitations of the mathematics. We can solve for almost everywhere. Okay. Yes. This is the example that I call the Johnny Cash example. It's the ring of wire.
What am I not getting?
What? You'll have to look it up. No, you can't. Tough, you're not getting it.
That face.
You ask one of the hipsters in the crowd to explain it. Okay. So that's a case that we can't solve for. But we can solve for half the space, and we can solve for the other half of the space. Almost half the space, and almost the other half of the space. And the reason that I chose this one is because it requires figuring out what kinds of boundary conditions we're going to apply, all right? So, out here, let's say in the upper half of this space here, so let's assume that this ring is in this plane, right? In the upper half of the space here, there's no current, and if there's no current, then the magnetic field, I probably should have included a curl relationship here. Remember, magnetic field is curl of A, and A is this, and A has got a J in it. So I can take the curl of this whole expression, and if J is 0, then the curl of B is 0. All right, and if curl of B is 0, then that applies. So in any space that doesn't have any current in it, just like in the Laplace's equation case, in any space where there's no net charge, no free charge, we can just apply Laplace's equation. Then that applies. So del squared phi d. And then once I have that magnetic potential, scalar magnetic potential, I can find the field by taking its gradient. And then it's only a question of deciding what series expression we're going to use for the solution. You know, 4 cases, I think. And you might be tempted in this case to say, well, that's got cylindrical geometry. No. Yes, it does. And so you might be tempted to try for cylindrical geometry. But actually, when you get far away, think about it, you get out here, and I look at my ring, right? And now I look back at it. We know that the magnetic field is going to look sort of like this, right? And so it might be this spherical geometry when we get far enough away. It would be a reasonable thing to expand in. And that's what I choose to expand in this case. And if that's the case, basically, I can use cylindrical or spherical or full spherical. I can use the spherical harmonics. All of them will apply. It's just a question of how many terms I have and how simple or how difficult it looks. So the magnetic potential as a function of r and theta, because I have this symmetry here, is going to be the sum L equals 0 to infinity of a sub L r to the L plus v sub L r to the minus L plus 1 P sub L cosine theta. So we just expand in Legendre polynomials, right? But we can say here that if we look at that, we see that the vector potential and the potential fall off as distance away from a finite source. So the potential is going to drop. It's going to go to 0 at infinity for this case. That means that I can get rid of all of those. Can I? Yeah.
Can't you only do that for the one outside?
What?
Can't you only do that for the one outside?
For the one outside. Oh, yeah. I'm sorry. I'm solving for that space above.
So,
Okay. So looking at it from the side, looks like this, and I'm solving up there. All that. Above the ring. Okay. I could solve inside the ring. I could do an only inside, all right? And I can solve only outside. But I'm going to solve over all possible R's above the center of the ring. Okay? All right, now comes the question of what other boundary conditions are we going to apply here. And this involves a trick. Okay, we've got to figure out what, some boundary conditions that we're going to apply. And what I'm going to do is say, well, I know the magnetic field already. We solved it already along that axis. All right, we know that. So I can start with that, and I can say, all right, the magnetic field along the z-axis is going to look like the current in the ring over c times 2 pi radius of the ring squared that. It's going to look like that. Okay? Not doesn't. This is not going to look like that. That's what it is. So I have the magnetic field along that line. And I need to make sure that whatever vector potential that I find leads to that magnetic field. All right? That field is the gradient of a potential. Right? And so it turns out that along that line then, the magnetic potential's got to look like this. I just have to integrate that. That's 3/2, that's 1/2. Right? So, I'm just thinking about the infinite case, and it looks like from that potential, when I take the gradient, the magnetic field's going to go to 0. I'm going to take a few minutes now to think about my limits here, right? While you take a short break, 5-minute break, during which Eli tries to talk to me, and I try to think about this.
Also negative sign.